Okay, here is page 1 of the addendum for integration. Number 13 from section 21D, which is the integration section. Find the derivative of cosecant, hence find the integral of cosine over sine squared. Okay, so first of all, remember that the cosecant is equal to 1 over the sine. So I'm going to rewrite it as 1 over sine because that would make it a little bit easier to find the derivative of. So I'm going to have 1 over sine x. I'm going to take the derivative of that. Remember that if I have something in the form 1 over something, that is equal to something to the negative 1. So I could do power rule on that, right? So instead of sine 1 over sine x, I'm going to write it as sine x to the negative 1, and then I'm going to do power rule on the outside of it. So I'm going to have negative 1 sine x to the negative 2. I just did power rule. And then I'm going to do the chain rule on the inside of that, which is going to be cosine x. And so my result is cosine x over sine squared x. And now we see how they got this. So if someone asked me to find the integral of cosine over sine squared x, since I know that the derivative of cosecant x is cosine over sine squared x, I know that if I was going to find the integral of this, if I integrated it, then I would end up with cosecant x plus c, of course. Okay? All right. By considering the derivative of arctangent of x, find blah, blah, blah. And remember, the derivative of arctangent x, as we found in the derivative section units that we just did. So remember that the derivative of arctangent of x is 1 over 1 plus x squared. And so if we were going to find the integral of something that kind of looks like that, then the integral of something that kind of looks like that would be something that kind of looks like arctangent. Okay? And the only difference between this and this is the minus 3, right? There's this times negative 3 here. So if instead of I have arctangent of x, is the derivative of arctangent of x is this, if I multiply this times negative 3, I just need to multiply this times negative 3 and they would be equivalent, right? So I would say that the integral of negative 3 over 1 plus x squared would be negative 3 times arctangent of x. And another way to think about it is, you say, okay, I'm going to factor this negative 3 out. I'm going to put it here multiplying out front. And so then I'm just going to take the integral of 1 plus x squared. And that would be, of course, arctangent of x. Okay, here we're going to take the derivative of an exponential function, and then we're going to find the integral of a similar exponential function. Remember that we know how to take the derivative of e to the x. Maybe you don't remember anything about the strategy for taking the derivative of something else to the x, a different base to the x. But pretty much you use this trick here. You're going to take the 2 to the x, the 2 of the 2 to the x, and you're going to expand it into this expression, which is equivalent to 2, right? If you do e to the natural log of 2, that's the same thing as 2. So if you put e to the natural log of 2 to the x, that's the same thing as saying 2 to the x. And now that we've done that, we can change. We could put e to the natural log of 2x. And remember, natural log of 2 is just a number. So it's kind of like saying, oh, if we have e to the 3 to the x, we could rewrite this as e to the 3x, right? And if you can write it in that form, then when you take the derivative of something like that, all you're going to do is do chain rule, right? Because it's basically like having 3x up there instead. Okay, so let's go back to the original problem. The derivative of 2 to the x, you can rewrite 2 to the x as e to the natural log of 2 times x. And then we're going to take the derivative of this. If we take the derivative of this, then we're going to end up with e to the natural log of 2 to the x, because the derivative of an exponential function is the same exponential function. But then you need to do chain rule. So you do the chain rule on the exponent, which is natural log of 2 to the times x. Remember that the coefficient natural log of 2 is what's going to remain after you do the chain rule on the exponent. So you end up with that. And then you compare that with the expression here, okay? Oh, let's rewrite the derivative here using this identity. So e to the natural log of 2 to the x is the same thing as 2 to the x. So basically this is natural log of 2 times e to, I'm sorry, not e, to the x. Okay? So I know that the derivative of 2 to the x is this. So the integral of this looks like 2 to the x also, but it's different by a factor. Okay? So like for example, I'm multiplying this by natural log of 2, and this does not have that multiplied. So it's almost as if I had divided both this and this by natural log of 2. And that would make a derivative integral pair, right? So the derivative integral pair that I have here, which is 2 to the x and then natural log of 2 to the x, can be modified by dividing both sides by natural log of 2. I would end up with 2 to the x divided by natural log of 2. Take the derivative of that, I would get 2 to the x. Okay, and now I have exactly what I have here. Okay, so the integral of that would be 2 to the x divided by natural log of 2 plus c. Okay, oh, by the way, the previous one, negative 3 arctangent of x, you would also have plus c there, right? Okay, number 16. By considering the derivative of x natural log of x, find the integral of natural log of x. Okay, so when I look at this, I think we got to do product rule, right? So the derivative of x natural log of x would be x 1 over x. Chain rule of x here would just be 1, so nothing. And then we take the derivative of x, and that would be 1, and then we multiply it times natural log of x. And this simplifies, obviously, to 1 plus natural log of x. Okay, so now I've defined that x natural log of x is a integral derivative pair with 1 plus natural log of x, right? Now, if I want to find a similar pair, but instead of 1 plus natural log of x, if I put 1 plus natural log of x minus 1, then what would be on this side? If I take the integral of this, it would be x natural log of x minus x, right? That would give me, if I took the derivative of this, it would give me this, right? So that's a pair. And then, but if you look at this, 1 minus 1, these two are going to cancel each other out, right? The 1 and the minus 1 cancel each other out. So basically what I found is that x natural log of x minus x is as a derivative integral pair with natural log of x. So if I say what's the integral of natural log of x, I can say that it is x natural log of x minus x plus c. Or if I wanted to, I don't know if it helps, but you can like factor out the x, okay? Either way is fine. Okay, so that was 16. Now we're going to go through some rules of integration by first looking at the derivative rules that we know. And we already went through these rules for the core. These are the additional derivatives that are covered in the HL sections. So remember, the derivative of cosecant x, we saw it up here. The derivative of cosecant is cosine divided by sine squared, okay? So it's, the derivative of cosecant is cosine divided by sine squared x, right? And you could also write this as cosecant x cotangent x. I just noticed, by the way, that actually this is this is actually negative, and this is negative. And let's go back up to the top because, like, do you see this negative here? I didn't propagate that, so that goes here and that goes here. Okay, so actually there's a negative there. I forgot. Sorry about that. Now, if we want to take the derivative of secant, remember that's 1 over cosine. So if we take the derivative of 1 over cosine, that would be negative 1 times the cosine to the negative 2, and then we take the chain rule of cosine in there, it's negative sine. So what we end up with is negative, or positive, because the two negatives cancel each other out, we have sine over cosine squared, which is equal to tangent times secant. Okay, so actually the derivative of secant x is equal to positive secant x tangent x. So there's a nice symmetry there where the derivative of cosecant is negative cosecant cotangent, and the derivative of secant is secant tangent. Okay, so let's do the derivative of cotangent. Remember, cotangent is equal to cosine divided by sine because it's the inverse, it's the reciprocal of tangent, right? So cosine divided by sine, let's take the derivative of that. So we'll use the quotient rule. So on the bottom, we'll have sine squared, right? And on the top, we'll have sine times the derivative of cosine, which is negative sine, minus cosine times the derivative of the bottom, which is also cosine. So basically what we have now is we're going to have negative sine squared minus cosine squared divided by sine squared. And the top, you can see, is negative sine squared plus cosine squared. Remember, sine squared plus cosine squared is 1. So this is negative 1 over sine squared. Negative 1 over sine squared is negative 1, or I'm sorry, it would be negative cosecant squared, right? Because 1 over sine is cosecant, so 1 over sine squared is cosecant squared. So basically, the derivative of cotangent is negative cosecant squared. Right. Negative cosecant squared x. Okay. Arc sine, arc cosine, arc tangent are, remember you do these with implicit differentiation. Basically the derivative of arc tangent is 1 over 1 plus x squared. The derivative of arc sine is 1 over square root of 1 minus x squared. And the derivative of arc cosine is negative 1 over the square root of 1 minus x squared. Okay? So that's it for the differentiation rules that are a part of HL and not SL. Now that we know these derivative rules, remember that if we were going to take the integral of each one of these, if we were going to do the integral, then each one of these would become the original function that we took the derivative of, so, except plus c. So like the integral of that would be cosine x plus c. The integral of that would be secant x plus c, etc. Okay? If we're going to take the integral of negative cosecant squared, it would be cotangent x plus c. Okay? This notation that I use here is my own notation, so don't like go off and do that in a math class later. Nobody will know what you're talking about. Okay. Let's move on. The derivative of tangent is secant squared, so therefore the integral of secant squared is equal to tangent x plus c. Okay, so that's just kind of what we were doing up there, right? And then finally we're going to do this problem, number 4. We're going to find the integral of these two here, and we just saw that the integral of secant squared would be tangent x, right? And what about sine? The integral of sine would be negative cosine x, right? Because the derivative of
The derivative of cosine is negative sine, so the integral of negative sine would be cosine. The integral of positive sine would be negative cosine. So this would be negative 2 cosine x, right? And then the integral of secant squared would be tangent of x. And then we just need 1 plus c at the end, okay, for both. All right? And if you want to check it, you know, it's hard to do integrals because it's a backwards derivative. Derivatives are easy to do, right? So you can check to make sure by taking the derivative of tan x, you know it's secant squared. The derivative of negative 2 cosine x would be 2 times, well, negative 2 times negative sine x, or positive 2 sine x, right? And then plus c, when you take the derivative of plus c, it just goes to 0. So if we took the derivative of tangent of x minus 2 cosine x plus c, we get secant squared x plus 2 sine x, which is what we started with here. So we've checked that our answer is correct, right? All right. And that's it for page 1.